All right, so we can create an energy diagram for this process, the process of sodium and chlorine coming together to form sodium chloride. All right, if we think about our energy, our collective energy of our sodium and chlorine before they react, that's right here, sorry. You can look in a little bit closer. Let's try to bring it in a little closer. Before they react, we can say this is where our energy is. And then, you know, it is an actual value, but we don't really care what the value is to start off with. What we care about is the steps and the energy required to make this reaction occur. And we talked about before how it's not just the ionization energy of sodium and the electron affinity of chlorine. There's also the lattice energy, and there's actually a few more things that have to occur. Before sodium metal and chlorine gas can come together, the sodium metal has to split up into gaseous sodium. And what do you think? Do you think that requires energy or releases energy?
To do what?
To convert the sodium metal to sodium gas, does that require energy or release energy?
Going from a metal to a liquid and then a liquid to a gas, that would require energy, right?
Very good. That's one way of thinking of it. If you go from solid to liquid and then liquid to gas, that's going to require energy. That's, melting and then boiling. Very good. And you can also see on the diagram here that it required energy. We had to move up in our energy level. Okay, it requires 107.8 kilojoules to convert that sodium from metal to gas. Once it's in its gaseous form, then it can interact with the chlorine gas. All right, almost. There's something else that needs to happen next. Next, we need the chlorine gas, here it is, chlorine gas, to become atomic, just chlorine atoms. Because in the end, it's sodium with one chloride ion, sodium ions with one chloride ion, not sodium with two, right? So you need to break that up, and that requires energy to break that chlorine-chlorine bond. And now here is the energy we talked about from the last slide, the ionization energy, and that requires energy. This one here, do you know what this energy corresponds to?
It says electron affinity of chlorine.
That's right. And does that process require or release energy?
Looks like it releases energy.
It does. That's right. And that's also what we said down here, right? That step releases energy. And what is this big, huge release in energy here?
That says it's the lattice energy.
Very good. And in the end, the lattice energy is the last step here. And now we end up with sodium chloride, which in the end is lower in energy than our initial reactants. And the difference between where we started and where we actually ended is our heat of reaction. That's how much energy, heat energy, the reaction released altogether. Okay, so these are those steps. We have sublimation of sodium, again, going from sodium metal to sodium gas, breaking the chlorine bond to make chlorine atoms, ionizing the sodium, ionizing the chlorine, and then forming that bond. All right, now let's look at this. What happens if we sublime the sodium, again, go from sodium metal to sodium gas, break that chlorine bond, same as before, but then this time we're going to give an electron to sodium as opposed to give an electron to chlorine. So chlorine this time is going to be oxidized and the sodium is going to be reduced. All right. The bond formation would be the same, negative 787. So you're still getting these bonds, or these ions to come together. Would that be enough to allow this reaction to occur?
What, you're saying make sodium chloride where the Na is a minus and the Cl is a plus?
Yeah, that's right. Do you think that? I mean, that's a fair question. I'm sure someday your kids are going to ask that question. If you have sodium coming together with chlorine, is there any way, it's a free world, right? Can't sodium decide, I would like to take the electron today, and chlorine can give up the electron. And then we can come together to form sodium chloride, right? I know this is a question that's always around our breakfast table. Why doesn't sodium ever take the electron? Why is it always sodium giving the electron? Isn't that kind of rude that sodium always has to give and chlorine always gets?
I have that same question sometimes.
Oh, you do? Very good. Excellent. So here's the answer. Here's the answer. The energy associated with sodium taking an electron, right, is now, instead of a 495 for the energy to release the electron, that's a positive value. Now, sodium, just like any other family, will take one child and be fine, it'll stabilize it, releases 53 kilojoules of energy when it gets that electron. So sodium stabilizes itself slightly by getting that electron, right? But chlorine, when it has to give up an electron, it requires 1,251 kilojoules of energy. That means this step here would be down 53 instead of up 495. Well, this step here would be the ionization of chlorine. And so it will go all the way up to not 400, not 800, 3 times as high almost. And then it would only come down 53. And so then the lattice energy would not be enough to make this reaction occur. Okay? So when your kids, do you have any kids, Fred?
We got one on the way.
Well, that's good. That's great. So when they ask, why can't sodium get an electron and chlorine give up the electron? The answer is because chlorine's ionization energy, right here, right, is just too large. For it to give up one of its children, its electrons, is very hard because it's so close to having a noble gas electron configuration. Okay, very good. So these are some of the parameters associated with the lattice energy itself. Okay, the lattice energy is dependent, the E value here, is dependent on these two Q's, which are the charge. So this is our lattice energy. It's dependent on the charge of each of the different ions. So if it's a +1 charge, then a 1 goes here. If the ion that's forming is a +3, it would go 3 here. And this is the charge of the anion, -1, -2, -3, whatever it is. Those go on top, divided by a constant and the distance between them. The distance between them, which is roughly determined by the ionic radius of the ions that form. All right, taking those two radii and adding them together would give you the distance between the ions. Okay, that's how you. Those are the parameters that affect the lattice energy. All right, so now we're in a point where we can look at electron configurations and determine the ions that will result from those electron configurations. The first electrons that are going to be lost when we form ions. So for example, I have this atom here, iron atom, and we want to know what kind of ion is iron going to form. +1, +2, +3, +4, +5, right? We want to try to rationalize the formation of ions that we do see. Now, do you remember by chance from your homework and stuff what charges iron forms?
It either forms a +2 or a +3.
That's right. Now, I think that we probably know that only from our experience with it, right? Our experience with problems, and we saw it in the book, but we don't really have a good explanation as why it can either form a +2 or a +3. But we really do now, and that is our electron configuration and our energy diagrams. Our orbital diagrams will allow us to see why it makes sense that iron can form a +2 or a +3 charge. So, ions generally will form by an atom losing its valence electrons. Now, let's see if we can write the electron configuration for iron. If I bring up the periodic table, can you write the electron configuration for iron?
I'll try.
All right. So, what's the electron configuration for iron?
Can we do the noble gas one?
Yes, let's do the noble gas one. That'll save us some heartache, right? So what's the most recent noble gas to the iron ion?
If you go from iron, that's 25 back to, no, 26, sorry. It's kind of small. Can you make it a little bigger?
Yes, I'll make it bigger for us. Okay, iron going from 26 back to what?
To argon, 18. So argon.
All right, that's our noble gas core.
And then potassium and calcium are 4s2.
Very good. 4s2.
And then 3p5.
3 what?
3d5.
Very good. 3d5. Excellent. 1, 2, 3, 4, 5. Oops.
Oh, 6.
Yeah, 3d6. 3d6. And this is the D block. Remember, you went down to 3, right? Because why?
Well, that's what you said to do. You said in the D block you go down 1.
That's right. The D block you do. You go down 1 n value when you enter the D block. Very good. So, 4s2, 3d6 is our electron configuration for iron. And the next question is, how many valence electrons does this iron have? How many valence electrons?
I can't remember how to do valence electrons.
Okay, so what you do is you look for the highest n value. Do you remember what the n value is?
I think so, but maybe you should tell me just so I know you know.
Okay, good idea. The n value is this value, the 4 or the 3 in this case, right? The n value is that number there. It's telling us the n value, whereas the s is trying to tell us the L quantum number, right? And this 2 or this 6 up here is showing us how many electrons are in the 4s subshell, where L equals 0. So n equals 4, L equals 0, and there's 2 electrons in that subshell. Okay?
Okay, so that means that there's only 2 valence electrons?
Okay, very good. So because there's 2 of these 4, there's 2 valence electrons. Now, we did have a name for these ones. Do you remember what those ones are?
I don't.
That's called pseudovalence. Remember?
Oh, yeah, pseudovalence. I remember that.
Okay, good. Pseudovalence electrons. So there's 6 pseudovalence and 2 valence electrons. Very good. So, with this information, we can predict what kind of iron would like to form. It would like to get rid of its valence electrons first. So the +2 charge, or the +2 ion, is what we would expect by it removing its valence electrons. Now, why would it form a +3 ion? Well, we'll look here in a second. There is stability gained when ions form half-filled subshells. Half-filled subshells, okay? So if we try to write the orbital diagram for iron, let's try to write the orbital diagram for iron, okay? So we have, this is our orbital diagram. Remember this? Energy, right? And we have our, this is, the axis here isn't really anything. It's just a space, right? But we start off trying to fill up this orbital diagram with orbitals. Remember, with little lines that represent orbitals. And we're trying to represent iron here. This is the electron, or the orbital diagram for iron, right? And I could just start off with iron, or sorry, with argon, and just kind of put a little argon box and then go up above it. And that's what I would recommend generally when you're trying to answer this type of a question. But for now, I'm not going to do that simply because I want to get a little bit of practice for us, okay? So we're going to write the whole electron or orbital diagram for iron. So the periodic table is helpful here. It can be nice and small because we don't need to have it to see the numbers necessarily. But what we're doing here is we're trying to follow along, starting with hydrogen, going to helium, lithium, beryllium, all the way along until we get to iron. And we're making ourselves an orbital diagram as we go, representing the subshells and the orbitals within those subshells with little lines. So we start off, hydrogen and helium are in a 1s. So I make a 1s line like that. So that is the 1s orbital. It's the one first shell, and it's the s subshell, right? And I know that because of the row here, first row. The second row starts off, this is my S block, right? So lithium and beryllium also go into 2s. And then after the 2s comes this is the P block, second row. So this is 2p. Now the 2p, remember what letter or number the P corresponds to?
I forget.
All right, do you remember any letters?
Yeah, S, P, D, and F.
Okay, S, P, D, and F are letters that help us relate are L values, and the L values here are 0, 1, 2, and 3. Okay? And now why that's important is because if we're talking about a p orbital, our L value equals 1, and that means the possible m sub L values are -1, 0, and +1. And remember, those m sub L values are telling us how many. The number of m sub L values tell us how many orbitals there are. So after the 2s comes the 2p, but we have to draw 3 because if L equals 1, m sub L, these are our m sub L values here, can have 3 different values, and that's represented by our 3 different shells within that subshell. Okay? So that's going to hold 6 electrons, again, because there's 2 electrons per each orbital, right? So we went from boron to neon. After that, we get to sodium and magnesium. What subshell is this?
Sodium and magnesium,
Yeah,
third row, so that's 3, and it's in the S block, 3s.
very good. So that's our next energy. And see, each time we get to one of these, we go slightly higher in energy, right? We're moving slightly higher. So after 3s is what?
Aluminum to argon, that's 3p.
Very good. So 3p, I put a little bit higher in energy than my 3s, 3p there, 3 orbitals within that subshell. What's next after 3p?
4s,
Very good. 4s.
and then 3d.
Very good. And then 3d. So I'll put my 3d over here. 1, 2, 3, 4, 5. Now remember, we did that because for d, L equals 2, and that means our m sub L values. What are the possible m sub L values if L equals 2?
-2, -1, 0, +1, and +2.
Very good. So we got 1, 2, 3, 4, 5 different m sub L values. That's telling us 5 different orbitals. Okay, now for iron, everything is filled up except for this last 3d isn't completely filled, right?
What do you mean?
Well, iron, we said, has 26 electrons. Is that right? Whoops. There's my sun again. Keep pointing to, there we go. Gotta get this bigger this way. Iron has 26 electrons, right? And so we need to fill this orbital up with those 26 electrons. We go 1, 2, 3, 4,
Oh, yeah.
6. Whoops. I'm not supposed to pair them up until I get to the end, right? But I knew they were going to fill. That's why I did that. So 6, 7, 8, 9, 10, 11, 12. Don't tell anybody I did that on accident, okay?
Oh, okay, I won't.
6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and now we have 26. Now I'm going to put little arrows, 21, 22, 23, 24, 25, and then I'll put the 26 there. I could have put that last one on any one of those 5 there. Degenerate, all the same energy, it doesn't matter. Okay, so what I have here then is whoops, a couple of these need a little more attention. What I have there is the orbital diagram for our iron ion, okay? And now really what I want to do now is focus in on my, what do you call it? My subshell, sorry, my valence electrons and my pseudovalence electrons. My valence electrons and my pseudovalence electrons, because these valence and pseudovalence electrons are where the atom of iron is going to do its chemistry, right? By losing these 2 electrons, what it does is it stabilizes, those are the valence electrons, it stabilizes iron, all right? And that's why an iron plus 2 ion, if I were to draw the plus 2 ion here, plus 2, the electron configuration for that, these would just be gone. And I would just have an empty 4s. All right? And if I go to a plus 3, what do you think happens? Where am I going to get that electron?
That last one over there.
That's right. This last one disappears. And now I have a perfectly full, or half full, perfectly half full 3D subshell. And when that happens, when you get a perfectly half-filled 3D subshell, you find a degree of stability. Anytime you can completely empty or completely half empty or half fill an orbital, there's a degree of stability that forms. So what we have here is not really, we could have predicted the +2 and the +3, and and that's fine. In some cases you can't really predict, but you can explain afterwards, right, why those ions exist. And that's powerful in itself. All right, that was great. Good job.